All right, let's get right into it. For decades, we've kind of been eavesdropping on the brain's electrical signals, this incredible symphony happening inside our heads. But what if we could go from just listening to actually understanding the language it's speaking? Well, that's exactly what we're talking about today. There's this incredible new AI model called Luna, and it's shaping up to be a universal translator for the brain. Just think about that for a second. What would it mean if we could truly decode the signals behind, well, everything? Our thoughts, our emotions, our health? This isn't some far-off sci-fi dream anymore. This is the real deal. It's the big question that's pushing forward some of the coolest research in AI and neuroscience right now. So how do we listen in on the brain? Well, the main tool for the job is the EEG. It's a pretty amazing piece of tech, really. You just place these sensors on someone's head and boom, you get this safe, real-time window into what the brain is doing. No surgery, nothing invasive. It's been a go-to for neuroscientists forever. But here's the catch. It's always had this one kind of hidden problem that's been holding everything back. And that brings us right to the core of the problem. For all the amazing things EEG can do, the data it produces has been a nightmare to analyze, especially when you try to look at a ton of it at once. It's like we've spent decades building this massive library of brain recordings, but we forgot to create a card catalog. It's just chaos. And this one single issue, it might sound simple, but it has been a massive bottleneck for progress. It's the reason scientists haven't been able to just dump all their data together and let modern AI do its thing. Find those hidden patterns in brain activity that could totally revolutionize medicine. Okay, so what is this problem exactly? The technical term is topological heterogeneity. I know, it's a mouthful, but all it really means is that, well, everybody does it their own way. One research lab might use, say, 32 sensors arranged in their favorite pattern, but then a hospital down the street uses 64 sensors in a totally different layout. You see the problem? It's like trying to read a dozen books at once, but each one is written in a completely different alphabet. And this right here just lays it all out, doesn't it? On one side, you've got what AI dreams about, data that's clean, standardized, all lined up perfectly. But then you look at the other side, and that's the real world of EEG data. It's all over the place, inconsistent, and let's be honest, it's just plain messy. And that chaos, that is exactly the problem Luna was built to fix. So you've got this total mess of data. How in the world do you solve a problem like that? Well, you build a universal translator. Let's dig into how this new model, Luna, actually creates order out of all that chaos. And here's our solution, Luna. Now, at its heart, it's what's called a self-supervised foundation model. All that means is that they just fed it a ton of raw brain data. We're talking over 21,000 hours of it. And Luna taught itself to find the basic underlying patterns of brain activity. Its entire job is to take all those different messy sensor layouts and, well, make them all speak the same language. So how does it actually work? It's really pretty elegant. First, Luna just takes in whatever messy EEG data you throw at it. It doesn't care about the layout. Then, and this is the clever part, it compresses all those different signals into one single standardized code. A unified language, basically. And finally, here's the real magic. The AI doesn't even look at the messy raw data for its analysis. Nope, it works entirely off that clean, standardized code it just created. The initial mess becomes totally irrelevant. And this is what gives Luna its superpower. It's topology-agnostic. That's just a cool way of saying it literally does not care how the sensors were placed on the head. It can see past the layout and understand the actual brain activity underneath. And what that means is it's universally compatible. Decades of old data we couldn't use before? Yep. All the new data we're going to collect in the future? You bet. It's a game changer. Okay, so the idea is brilliant. The theory is beautiful. But you know what really matters, right? Does it actually work? Let's get into the results, because honestly, they are pretty staggering. First up, let's talk speed. We're looking at a 300 times reduction in computation. Let me say that again, 300x. That's not a typo. To put that in perspective, a study that might have taken a whole month to process could now be done in just a few hours. This makes huge brain research projects not just possible, but actually practical. And it's not just faster, it's also way less resource hungry. It needs up to 10 times less GPU memory. Now, why does that matter? Well, it's huge. It means you don't need a crazy expensive supercomputer to do this kind of work anymore. It opens the door for so many more labs and researchers to get in on the auction. Okay, so it's fast and it's efficient, but is it any good? Is it accurate? The answer is a resounding yes. On a key test for spotting abnormalities in brainwaves, Luna scored a 0.921 AUROC. Now, what does that number mean? Think of it this way. A perfect score is 1.0. A score of 0.5 is just random guessing. So 0.921, that is exceptionally good. It's truly state-of-the-art performance. And this quote right here, this is the real kicker. It pulls everything together. Because all these amazing results, the speed, the efficiency, the accuracy, it's not just on some perfect cherry-picked data set. No, these gains were consistent across every single one of the messy, real-world electro layouts they threw at it. Bottom line, the universal translator works. So, look, the tech is obviously a massive breakthrough. But let's zoom out and ask the big question. What does this really mean for us, for the future of brain science? Okay, this is where it gets really exciting because the potential applications are just incredible. Because we can finally analyze all this diverse data together, we can start building way better tools for things like spotting neurological problems earlier and more accurately, or creating new tools for mental health, maybe even ones that can recognize emotional states from brainwaves. The list just goes on and on. There are probably uses for this we haven't even thought of yet. And that really brings us to this one final, pretty profound thought. For the first time, we have a tool that's starting to become fluent in the brain's native electrical language. The technological barrier is starting to crumble. So the real question isn't, can we understand it anymore? The question is, now that we can listen in, what are we going to ask?